Hey everyone, today we are going to go ahead and implement the generative adversarial network. So in the previous video, we actually took a look at the little bit of the derivation of where does the GAN loss come from, what are some of the main ideas, all that sort of stuff. And so if you want some more details of all of that, just go ahead and take a look at that previous video. But today we're just going to do an implementation. I'm going to walk through a couple of details that I think are really important when it comes to the GAN, especially how we manage the gradients. It's honestly one of the most challenging parts of it, but we'll get through it. And so let's go ahead, just do a quick recap of what is a GAN. A GAN, or the Generative Adversarial Network, is in its name a generative model. And it's a generative model that kind of plays a game of cat and mouse is the way I like to think about it. And that's because there's two parts of the architecture. The first part is the generator. The generator's goal is to take some random noise and generate some fake data. And this whole concept of generating from random noise should feel familiar because in the variational autoencoder, that's exactly what we did. The encoder took data, compressed it down. We then compressed down to a Gaussian latent space. So we then sampled noise from that latent space, and we generated the decoder basically took that and regenerated the data, right, with the reconstruction task. And so in the same way, instead of having a encoder decoder structure, we essentially just have a decoder, something that takes noise and generates. And so that's the first part of the GAN architecture, the generator. And its goal is to generate fake data. But instead of using some type of a reconstruction task like we did in the variational autoencoder, we're now using something known as the discriminator. And the discriminator is exactly what you think. It takes in real data from our real data set. It takes in fake data from our generator. And its goal is to identify which samples are real and which samples are fake. And so the discriminator is fighting against the generator, and the generator is fighting against the discriminator. Because if you imagine, if we have both neural networks in tandem, they're kind of doing opposite things. The goal of the discriminator is to be able to identify real versus fake data. The goal of the generator is to generate data that's so good that the discriminator is unable to distinguish between them. So this is what makes it adversarial, because they're essentially battling against each other. And all of this is handled by the binary cross entropy loss. So the way you should think about it is, and the way we're going to set it up is real data. If it's a binary problem, then we'll have class labels, right? And in this case, we'll say fake is 0 and real is 1, but you can do it the other way as well. It doesn't really matter what number you use to assign to real and fake data. But our discriminator's goal is to maximize the log likelihood of the probability. Again, some of these details I have in my previous video. So again, go take a look at that if you're a little bit unsure. But the main idea is that the discriminator wants to get really, really, really good at identifying real versus fake. And it does that by minimizing the binary cross entropy loss or maximizing the log probabilities of our classes, right? That's the main idea. The generator, on the other hand, wants to maximize the loss or minimize the log probability. What does that mean? As the generator gets better and better, the discriminator will be unable to distinguish between them because the real data and fake data look so close to each other that the discriminator is no longer able to tell. And so this is kind of antagonistic, right? It's exactly the opposite of what we're trying to do. So the discriminator is trying to make the loss go down, and the generator is going to try to make the loss go up. And the way we set this up is we essentially train both models one at a time. And we're going to kind of see this iterative training approach in just a bit. But that's the key idea. Everything is managed through the binary cross entropy loss, and the discriminator is trained to minimize this loss, and the generator is updated in a direction that most confuses the discriminator, or where the discriminator gets worse. We're going to see all of that in just a bit. So in that previous video, we basically went through this derivation to understand a little bit about what is going on in the GAN, how does it work, and we ended up, let's make it a little bit bigger, we ended up with this final loss function, where your loss function is basically you're trying to maximize your log likelihood of your loss, and that's what the discriminator is trying to do, maximize the log likelihood, and the generator is trying to minimize the log likelihood. So we have this min-max game essentially occurring. Now this does lead to some things like training instability, mode collapse, things like that I'll kind of briefly discuss and maybe we'll get to see. But for now, we can just go ahead and start building pieces of this model and just see how it all comes together. So we're going to be doing a very simple example today on an unconditional generative model. Unconditional generation is basically every time I want to generate something, it will generate something random. It'll just generate, in this case, just one of the digits. But I have no control over which digit does it generate. In the next video, we'll do an example of a conditional generation problem where we can actually say, oh, I want to generate the digit 2, I want to generate the digit 5, whatever it may be. So let's go ahead and start. So we're going to need import numpy as np. We're going to need torch, import torch.nn as nn. We'll need all our standard from, oh, we don't need that. So let's go ahead and do from torch vision.datasets, import mnist. Just for today, we'll do more fun datasets later on once we set some of this baseline. From torch vision, import transforms. We need from torch.utils.data, import our data loader. We need import torch.optim as optim, and then just some plotting function. So import matplotlib.py plot as plt, and from tqdm.notebook, import tqdm. So these are all the imports we're going to need, nothing too crazy. And so what we're going to do is implement a simple linear unconditional mnist GAN. Lots of words there. So what that means is we're basically going to have to define two different neural networks. The first one is the discriminator, and the second one is the generator. So let's just go ahead and define both of those and set it up that way so we can ignore all of the math. Again, take a look at it if you want to from previous video. So if we remember, our images in MNIST are 28 by 28 pixels, which means they're 784 dimension vectors, right, when we flatten them. So let's go ahead and write the discriminator first. Let's do class MNIST discriminator, and then dot module definite self. And this self doesn't really need anything. Super.init. There we go. And so what we're going to do is just define self.discriminator is equal to nn.sequential. And I've just arbitrarily picked something here. So I'm going to do a linear layer. And this is going to be 784 by 1024. And then we're going to do, and there's a couple of little details when it comes to GANs. You're going to see a couple different implementations of it that we're going to see, and I'll kind of try to mention. It seems to work best for GANs, especially when our discriminator is using leaky ReLU rather than ReLU. So that's what we're going to do. This is just empirically has been shown that leaky ReLU activation seems to work really well for GANs. And this has to do with GANs are typically a very unstable training regimen that we're going to kind of talk about a little bit later. But leaky ReLU seems to allow that negative gradient to flow through where ReLU just zeroes everything out that's under 0, right? So we're going to be using leaky ReLU and just keep it simple. So we're going to do leaky ReLU. I'm not going to talk too much about details of kind of why. It's mostly just by practice. So, and we can throw a dropout in here with 20% dropout, whatever. And so then we're going to repeat this. So yeah, we're not going to discuss too much about why just now. We just want to keep this simple to get you started to understand kind of the more big picture details about GANs, and then we'll talk about these little details in future videos. So for now, we just have a stack of linear layers. We're using leaky ReLU because it seems to, again, work better, and then dropout for obvious reasons to help with overfitting, that sort of stuff. And so we're going to go from 784 to 1024, then I can go 1024 to 512, and then we can do 512 to 256. And then the last one's going to be nn.linear 256 to 1. So why are we just outputting one number? And that's because we are doing the binary cross entropy loss, right? So remember, the discriminator is basically going to output a single number, and it's going to be the raw logit of the output. And then we apply what we don't apply, but our loss function will apply the sigmoid to that. So it's going to be some number between 0 and 1, which is what our binary cross entropy loss wants. If we had two outputs, then we would have had to use categorical, just regular cross entropy. But today we just have, we're using BCE loss that expects one number output. So we have one output here, so no problem. So that's our final linear layer, and we are good to go. So forward, self, x, and we can do our, let's say the batch size is x.shape 0. Right, so how many samples do we have? Then we have x equals x.reshape. So remember, our images are going to come in as image shapes, like so it'll be batch by channels, by height, by width. We just want to go ahead and flatten them. So we can flatten by doing batch size -1, right? Just go ahead and do that. So that'll flatten us from, batch by one channel by 28 by 28 to just batch by 784, which is what we expect right here. So there we go. And then we're going to do return self.discriminator x. And that's it. That's our discriminator. So the discriminator takes in our feature vectors of length 784, which is flattened images, and produces one number, because the goal of the discriminator is to say what is the probability that this is real, or what is the probability that it's fake, right? That's the main goal of the discriminator. And then similarly, we're going to have a generator, and the generator works like this: mnist generator, and then dot module definite self, or not x, sorry. Here we're going to have to add a latent dim. So here's another kind of question that you have to ask yourself of when we pass in random noise, it's a noise vector, and it's completely up to you what dimension noise vector you pick. This is random noise from the Gaussian latent. So we're sampling from a Gaussian latent space. That means if we have, if we pick z to be 100, that means it's a 100 dimensional Gaussian vector. And the generator can pick however it wants to cut up that Gaussian latent space to actually generate the different types of data that it wants to. So the larger your feature vectors here, right, the larger the noise vector we pick here, the more fine generative capabilities it can do, because it's starting from a higher latent space, right? So it can kind of mess and disentangle that vector space however it wants to. So we're just going to pick 100, I believe, just to start with. Whatever it is. But yeah, we're going to go ahead and do that. But again, this is like a hyperparameter. You can test with different ones to see how it works out. And again, thinking back to the variational autoencoder, we compress down and then decompress. And so what is the latent space that you want to pick for that compressed representation? That's kind of the same intuition you can use for how much or how little dimensions do you want to use for your random noise. So let's go ahead and do that. So this is going to take some latent dim. Going to be, again, we need the super.init, and then we're going to do self.generator equals nn.sequential. And then very simply, we're just going to do a stack of linear layers again. So it's going to be nn.linear, and it's going to start from the latent dim, and it's going to go up to, let's say, 256. And then for the same reasons as before, we're going to throw some leaky relus in there along with some dropouts, right? So it's going to be nn.leaky relu, and then nn.dropout. I'll say p equals 0.2, right? It doesn't really matter. You can pick whatever you want. MNIST is, again, such a simple data set that basically anything works. I'm just going to stack a couple of these together. And so we're going to have this, and then it's going to go from, let's say, 256 to 512, and then let's say 512 to 1024, and then we're going to do the last one to be nn.linear 1024 down to 768, right? Because this is the final, we know our MNIST images are of dimension 768 or 28 by, or sorry, not 768, my bad, 784, because they are 28 by 28. So there we go, the 784. So that's the entire setup. That's our generator. And notice that the generator will create feature vectors of length 784, and our discriminator accepts feature vectors of length 784. So, everything's kind of lining up there. Now, one small caveat we want to keep in mind, it's completely up to you, but if your images are between 0 and 1, right? So if your image pixel values are between 0 and 1, then you'll want to throw a, I need a comma here. You'll need to throw a nn.sigmoid right here, right? So sigmoid will ensure that the output values of these pixels are between 0 and 1. That would be totally fine if you want to do it that way. If your images are between -1 and 1, which is how ours will be, because I like having the center at 0 and then kind of spread between -1 and 1, then we want to use the tan-h here as well, instead, tan-h. So this is the tan hyperbolic. We'll go ahead and scale everything between -1 and 1. And so let's go ahead and write our forward function, def forward self x. Again, batch size is going to be, and actually this won't be x, it'll technically be the noise vector, right? We pass in some noise vector. And so batch size is going to be noise.shape 0. So we have that. And then we will do generated is equal to self.generator, right? We're going to pass into our generator our noise. And then we're going to take our generated is equal to generated. And we just want to make sure it's in the same shape as our original data. So we're going to do dot reshape. And we know it's going to be batch size. And then I could make this more dynamic, but I know that MNIST is going to be 1 by 28 by 28. So there we go. And we can then return generated. And we are good to go. We now have our discriminator, we have our generator, and it's as simple as that. We're going to keep this as simple as possible today. And so now that we have all of this, let's go ahead and start setting up our training stuff, right? So we're going to do that first, and then we're going to talk about how we control backpropagation, because I think this is the most challenging part of just keeping in mind. Not challenging to implement, just challenging to to just how to keep some things in mind. So let's go ahead and kind of set things up. Our latent dim is going to be, let's say 100. So we're using 100-dimensional noise vectors. We're going to say batch size is 64. We're going to say device is equal to CUDA if torch.cuda.is available, else CPU, right? So that's fine for now. And then epochs, let's say is 200. We're going to train for 200 epochs. And so here's the most important part of the GAN training. The GAN training is split into 2 steps. You have the discriminator step and the generator step. So we don't train the discriminator, or when I say train, we don't update the weights of the discriminator and the generator at the exact same time. We don't do that. We do them one at a time, and we iterate kind of doing them one at a time. So the way we do this is, let's first talk about the discriminator step. You can obviously do whichever step you want first, it doesn't matter, but let's just start with the discriminator step. And so what the discriminator does is you take some noise, and actually let's kind of think about it this way. Let's start at the end, actually. That'll make it easier. So we give our discriminator some real data and some fake data, right? We give it some real data and fake data. So some simulated data that we've generated and some real data. That goes to the discriminator, and we compute the binary cross entropy loss here. And what we want to do is we want to make sure the discriminator minimizes the BCE loss. Right, so that's the most important idea. And so that means we're going to backpropagate this loss to the discriminator. So the discriminator is trying to minimize that. What we want to make sure we don't do is backpropagate this loss through the discriminator and through the generator. That's a huge no-no, because that would mean the generator is also being updated to minimize the BCE loss, which is not what we want to do. The generator should be maximizing the BCE loss. And so this is why this is so important. We only, in the discriminator step, we only train the discriminator and we don't update the generator. There's a couple of ways you can implement this. The easiest one is leveraging PyTorch's detach. So what we're going to do is generate some data, create some fake data, and we have our real data. But before passing our fake data to the discriminator, we're going to detach all of its gradient information. So basically it forgets that it went here. And so when we do backpropagation, the backprop will not continue on to the generator. This is one of the most important steps. And this is one of the most common bugs too that you'll see when people write the GAN training paradigm, because they're going to be backpropagating this loss through the discriminator and through the generator, and that'll mess everything up. So you don't want to do that. So the discriminator step, we only want to update the discriminator by backpropagating this BCE loss through the discriminator, and that's it. Nothing else gets changed. So you can see it's red here. We disable that update. When we train the generator, what we do is we compute the BCE loss. And now what we want to do is the generator should maximize the BCE loss, right? We want the BCE loss to get worse. So that means we don't really have a choice. We have to backpropagate the BCE loss through the discriminator and then through the generator. We have to go through all of it because, again, to get to the BCE loss, we have to go through the generator and through the discriminator. And there we go. We're at the BCE loss. The key idea, though, is when we backpropagate through the discriminator, we only want to compute the gradients of the discriminator. So the generator knows, how do I maximize my BCE loss? Right? So it pretends the fake is real. So GZ learns to trick dx. So we train the generator to trick the discriminator by updating the generator in the direction that maximizes the BCE loss. That's the critical idea that I want you to keep in mind. But when we do the backpropagation, we will only update the generator. So we won't update the discriminator. So sure, we computed gradients, but we won't change any of the weights of the discriminator. The weights of the discriminator will be left alone, but we will compute the gradients. And that's a key idea. So we have to kind of disentangle the notion of computing gradients and updating weights, which is, again, how PyTorch works, right? We do a loss.backward, that computes gradients, but then optimizer.step actually updates the weights. And we just need to make sure we're organized about how we do it. Otherwise, you're going to be giving the wrong loss to the wrong model, right? We want to make sure when we're minimizing the BCE loss, that goes to the discriminator. When we're maximizing the BCE loss, that goes to the generator, and not the other one. So that's the key idea. So there's actually a lot of ways you can technically implement this. The most common way is just to have two different optimizers. So let's go ahead and do this. So our generator learning rate, let's just say 0.00 whatever. It doesn't really matter. Again, this is a very simple data set, so you can basically do anything you want and it'll work. One thing to keep in mind is you might want a generator that learns faster than the discriminator, or vice versa. This is all kind of, you have to experiment and see what works. So just some kind of, there's more details that we can look at, but for now we're going to keep it simple. Same learning rate. And so we'll have our generator is going to be our MNIST generator, right? It's going to take in the latent dimension. We're going to put it on the correct device. And then the discriminator is going to be, again, MNIST discriminator. This had no arguments, and we're going to make sure it's on the correct device. Looks like I just called it latent dim, so let's just do that. Looks like there is no leaky ReLU. Is it because leaky ReLU is... yes, leaky ReLU has an uppercase U, so let's just update all of you, and we should be good now. Okay, good. So if we quickly check generator, right, there we go, stack of generator layers, discriminator, stack of discriminator layers, and we're good to go. Simple as that. And what I meant is we now want to have two optimizers, one for the generator and one for the discriminator. We could also just do it with one optimizer, but then the code becomes a little bit more complicated because when we do optimizer.step, we have to make sure that optimizer.step only updates the parameters that we care about. Not that you couldn't do it, it's just a little bit cleaner to have two different optimizers. So we're going to do gen optimizer is nn optim. Let's do optim.atom. We're just going to use the standard atom optimizer today because it works. Later on, when we look at the Wasserstein GAN, we'll see that at least they found that the momentum-based optimizers don't seem to work as well for that specific loss function. So we're going to have to use some other loss functions at that point, but today we're going to use standard stuff. There is another thing that we can update here that I'm not going to really worry about yet, but there's something known as the beta parameters in your Atom optimizer. It's basically how it weights. So if you know a little bit about Atom, it's kind of like a weighted average of previous gradients and current gradients, and it allows you to smooth your gradient transitions as you go from basically go from iteration to iteration. We'll talk about this in more specificity later, but you can control how much weighted, like past information and current information do you want. Typically the betas are set to like 0.5, 0.999. We'll talk about why we do that later. For today, we're going to just stay with defaults, right? We're not going to mess with anything. So there we go. Let's go ahead and keep that. And so let's go ahead and now do our tensor to image transforms. But it's going to be standard transforms.compose. And this is just going to be transforms.toTensor. Right, so we're going to convert our images to tensor, and we just want to normalize them, right? And remember, we wanted our images to be between -1 and 1. That's why we applied the tan h at the end of our generative model. So if we want it between -1 and 1, and our images, when you can do two tensors between 0 and 1, that means we can just subtract 0.5 and divide by 0.5, right? So if we have, let's see here, if we have -1 to 1, if you subtract 0.5, then that will be, we start with 0 to 1. If you subtract 0.5, then it will become negative 0.5 to 0.5. And then if we divide that by 0.5, that'll become negative 1 to 1. And so we just need to subtract by 0.5, divide by 0.5, and we're good to go. Or we can subtract some mean and some standard deviation and just let it do it for us. So we can use transforms.normalize and just use a 0.5 mean and a 0.5 standard deviation, just like that. So that's my simple transforms. And so our train set is going to be mnist. Let's see, I already have it saved at this path, but you can pick whatever path. You could pick whatever path you want. There we go. Transform is equal to tensor to image transforms. There we go. That's our train set, which means our train loader, our data loader, is going to be the data loader. And it's going to be our train set. Batch size is going to be whatever batch size we set, and shuffle is, of course, true. And we're good to go there. So now let's go ahead and write our, again, training function. And this is going to be the most important part of the whole implementation, right? Because everything we've done so far shouldn't seem all that new to you, but this is where we're going to kind of manage some of that gradient information and all that. So we're going to do def train unconditional GAN is what we'll call it, because next time we'll do a conditional GAN. So we have a generator, right? What is our generator model? Our discriminator, what is our discriminator model? Our generator optimizer, our discriminator optimizer. We'll have our data loader that we want to train with. We have epochs. We have our device, right? What do we want to train on? By default, let's just set this to CPU, whatever. Let's set some defaults here. Let's say our epochs is 200, device is CPU. We'll have a plot generation frequency. So every 50 steps in this case, or 50 epochs, we'll plot something so we can see what the generations look like. We'll have our plot loss frequency. Every once in a while, we'll kind of print the loss out to see how things are going. And then lastly, num gen. So every time we plot images, how many pictures would you like to generate? So we'll just kind of keep some of that information there. And so the first step, what is the loss function? It's going to be our binary cross entropy loss. So it's loss func. It's going to be nn.bce. And here's the key part, with logits loss. So the reason we're doing BCE with logits loss is because, if you remember, our discriminator right here returns raw logit. So basically whatever the output of the linear layer is. Notice there is no sigmoid here to convert that logit to a probability. If we had done nn.sigmoid here, then we just use the standard BCE loss. We wouldn't do BCE with logits loss. Completely up to you. You can obviously pick either one and they'll both work. It's just if you use BCE with logits, then we don't want to apply sigmoid. Otherwise, if we have a sigmoided output from our generator, the BCE with logits will apply another sigmoid to that sigmoid, and that's obviously incorrect, right? So we want to make sure we don't do that. Good. So now we're going to do gen losses, disc losses, just so we can store some of this information as we're going. We're going to do for epoch in TQDM range epochs, right? So how many epochs do we want to train for? And we're going to do generator epoch losses, and then our discriminator epoch losses, so we can store our per epoch losses and average them up at the end to see how things are going. And then lastly, we're going to do for images blank in we don't need that, so in data loader. So we're going to loop through, and of course our mnist will return images and labels. Because we're doing unconditional generation, we don't need any labels for today. We'll look at that next time. For now, we're just going to do our images. And so let's just go ahead and store some information. So batch size is going to be our images.shape 0. Remember, our images are going to be in the shape of batch by channels, by height, by width, where it's going to be basically batch by 1 by 28 by 28, because that's our mnist shape. So now that we have that, let's make sure our images is on the GPU. So images equals images.toDevice. Just make sure everything's in the correct place. And we are good to go start. So first we're going to do is train discriminator, right? That's the first step. And then we're going to train generator. generator. You can do, and you could have done it in the opposite order as well. That would be fine. But we're going to just do it in this order today. Step 1, we need to sample some noise, right? So the entire GAN, we start with some noise. So let's go ahead and generate noise in the shape that we know it should be. So we're going to generate noise, and it's going to be torch.rand n, because we want it to be Gaussian noise. If we do rand, it's uniform. Rand n is normal or standard Gaussian. And we're going to generate from a width of the shape of batch size by our latent dimension. So I believe, okay, so it's just latent dim, because that's what I called it earlier. So latent dim. So I've generated some data here, some random noise, and that is what this will be, this random noise vector. It's of batch size by whatever the dimension vector that I wanted was. In our case, it was 100 or whatever. And when I generate something, I need to make sure it's on the same device, right? So device equals device. I want to make sure it's on the same place where everything else is, otherwise it'll throw the, hey, something's on the CPU, something's on the GPU error. And so now that we have that, the next step, so what are we doing? We have batch size number of real images. This images here is real data from my real data set. I now have a noise vector here, which I'm going to use to generate fake data. We just haven't gotten there yet, but we're going to be generating fake data with this. So what we're going to do is we need some labels, right? Because this is binary cross entropy loss. So that means we have zeros and ones for what it is. So we're going to say generated labels. It's going to be torch.zeros. And it's going to be of shape batch size by 1. And device equals device. So what is this? This is I'm saying that the correct label for all of my generated data, which you'll see how we use this label later, all the correct labels is 0, because we're saying, if you remember, we said that generated data is 0. In the same way, our real data, so true labels, is going to be torch.ones, batch size by 1, device equals device. So again, we're making sure it's on the correct GPU, CPU, whatever you're training on. But all I've done is created some labels here. I have my generated labels, which is my 0. So I'm saying the generated is 0, and my true is 1. And that's it. So I've just created some fake labels here for me to use for every sample in the batch. So this means our loss is actually computed over, if we have 64 images in our batch, that means we have 64 real images, and I'm about to generate 64 fake images. So I have 64 zeros for the fake generated images and 64 ones for my real images as well. So these are just class labels for our future loss computation. Now that we have that, let's go ahead and generate some new samples. So now we're going to actually leverage that generator. So we're going to do generated images is going to be our generator. We pass in the noise, and then, and that's it. We're just gonna leave it like that for now. We're gonna add another detail to that in just a bit. And so now it's time to actually compute our discriminator loss, all that stuff. So our real discriminator, and let's do some labeling here. So this is going to be create labels for discriminator, call it that. Generate some samples, right? Generate some data. So that's our fake data that we've created. And now we can compute logit for real and fake data. So what we're going to do is take our real data, pass it through the discriminator, and we're going to take our fake data, pass it through the discriminator. So it's going to be real discriminator pred. And this is going to be our discriminator. And we're going to pass in our real images, which is just images. And then we'll have our gen discriminator pred. This is going to be our discriminator. And now we're going to pass in our generated images. So notice how we're passing into our discriminator our real images and the fake images, which is exactly what we had in the visual here, right? In our discriminator, we pass in real data and we pass in fake data, except we could have also concatenated them and passed them in together, but let's just keep it simple. We can just pass them in one at a time, and in the end, it doesn't really matter. It's the same thing regardless. So that is our setup. We've now computed raw logits. Basically, what does our discriminator predict about the real images versus the fake images? Now that we have that, let's go ahead and compute the loss, right? So compute loss. So what we need to do, compute, obviously there we go. There's a couple ways we could have done this. We could have concatenated it all together and done it once, but we can just compute the loss for the real, we can compute the loss for the generated, and average them together. That's one way to do it. Or we could concatenate the real and the generated, and then our true labels, generated labels, just put them all together and just give it to the loss in one go. It would average anyway. It doesn't really make a difference whether we do them in 2 chunks or just do it in once and then it's done. So we'll do our real loss is going to be our loss function, the binary cross entropy loss. So we with logits that we defined earlier, real discriminator pred, right? So we're passing our discriminator for the real discriminator, right? The real pictures, basically for the real pictures, we want it to predict that these are real. So it gets the true labels. So that's the loss function. For the images that are real, our discriminator should predict that they are real, the true labels. That's the key idea. And then for our fake loss, it's going to be the loss func. For the generated images, so whatever the discriminator predicted for the generated images, it should predict that these are fake. So these get the generated labels. So that means for our discriminator should predict 1 for real and 0 for generated. We could have also done it the other way around. It could have been 0 and 1 or 1 and 0. It doesn't matter. You can pick either or because it's symmetric anyway. So there we go. So that is our setup. That is us computing the loss, making sure our discriminator is learning to predict 1 for the real images and predict 0 for the generated images. Now that we have both of them, we can go ahead and do our discriminator loss is going to be our real loss plus fake loss divided by 2. Let's just average them together. Like I mentioned, we could have also done another way. I'll just write pseudocode. We could do torch.cat, and we would have concatenated together our real disc pred and gen disc pred, and then we would have done torch.cat, and we could have done our because we did real first and gen second, that means we'll put in true label first and then gen label second, right? And this would have been and then we would have done the loss between this, and these would have been the target labels, right? And this would have also taken an average, so it's exactly the same thing. So we're just doing it in 2 steps here. That's our discriminator loss. And now we're going to do, let's just go ahead and store that. Let's save that. Discriminator epoch losses dot append discriminator loss dot item, just like that. And so now we can do our update, right? We want to update the discriminator. Discriminator optimizer dot 0 grad discriminator loss dot backward, and then discriminator optimizer dot step. And here is where it becomes a little bit complicated. This should be backward. And why it's important to keep this in mind. So we have 2 optimizers. Remember that. We have one optimizer that only sees the discriminator parameters, and we have one optimizer that only sees the generator parameters, right? That's the key idea. And we had 2 different optimizers. Now I've just done the discriminator step, so I just called discriminator.backwards. So that means I'm going to compute gradients through here and through all of this, because I never added any detach yet. We'll get to that in a second. But I just computed gradients for the entire computational graph through the discriminator and through the generator. But now that I've computed these gradients, going through all of this, the discriminator optimizer.step. So we only updated the gradients of this one right here, of the discriminator right here. Or we updated the parameters of the discriminator using the gradients. We have gradients computed for the generator, but we didn't use them because we never did generator optimizer.step. So this one is left alone, but there's gradients here. So there's 2 ways to handle this, and we're gonna just do both of them for sanity's sake. The first one is that when we go to update the generator in the next step, we need to make sure before we compute gradients, we zero it out. We have to make sure we zero out the gradients, because if we have gradients computed here from our previous step, right? We just computed gradients on everything. So if we have gradients on everything, then if we go to compute gradients again for the generator step here, that means we're going to accumulate together the gradients from the previous step and the current step. And that's a big no-no, right? We don't want to do that. We don't want to mix gradients between the two steps. So option 1, we make sure before we update the generator, we zero the gradients out ahead of time before we compute any new gradients. And it'll be exactly the same thing for the discriminator, because when we do the generator step, we're going to compute all of these gradients. We're going to compute gradients for everything, for the discriminator and the generator, which means when we go back to the discriminator step in the next step, right? So after we do the generator, we'll go back to the discriminator. When we compute this gradient again, we're going to accumulate the gradients from the previous step of the generator and the new step of the discriminator. So see how we're again mixing gradients together? So it's important that we make sure we zero out the gradients for the model we're about to update before we compute new gradients. And that's why you see here, I have a discriminator optimizer.zeroGrad. I zeroed out the gradients before I computed the backwards. And this is such a small detail, but such an important detail to keep in mind. The other thing we can do is, especially when we're computing gradients, let's put that back, especially when we're computing gradients for the discriminator, we don't need any of this. We don't need it to backprop through any of this stuff. That's just wasted computation, right? If we call .backward just needs to end at the discriminator. We don't need it to go to the generator, which means we can actually generate some fake data and then take it off the computational graph, do a detach. So that means when we do backprop will end right here. It won't go onto the generator because it's wasted compute to compute these gradients right here on the generator that we never end up using. We don't care about them. So a common thing that we will do is when we generate some data here, let's just go ahead and do .detach. Go ahead and detach them. And this will make sure that when we call loss.backwards right here, we'll have gradients that go through these loss values right here, and it'll go through the discriminator here. But the generated images that I passed into the discriminator are detached. So that gradient information will not continue flowing back into the generator because we have no need for that information. We're only updating the discriminator here. And this is such a crucial but tiny detail that I wanted to make sure we hammered home. All right, so now let's go ahead and do our next part. To update our generator, how do we do it? We generate some data, pass it to our discriminator, get our BCE loss. And we'll kind of talk about exactly how that works in just a second. But for now, let's go ahead and do it this way. We're going to do noise is equal to, so let's just generate some new noise again, torch.randn, batch size by latent dim device equals device. So we've generated some noise again, and now we're going to go ahead and generate some new images again. So generated images is equal to generator noise. Right, so there we go. Now that we have all of that, we can do discriminator pred, right? So what does our discriminator think about these generated images? That's going to be discriminator, and we're going to pass in our generated images, just like that. And so now that we have that, we can go ahead and compute our loss. And this is the most important part, that we are now training the generator. The generator's goal is to fool the discriminator, right? That's the entire purpose of this architecture, which means our loss should be, our generator loss is going to be the loss function. So same binary cross entropy with logits loss, all that stuff. It's going to be on the discriminated pred. But what do we want it to predict? This is the key idea. Earlier, when we were updating the discriminator, we wanted to make sure when the discriminator got a real image, it predicted it as real, right? It should predict that a real image is real. And we said that we wanted to make sure that when we gave it a generated image, a fake image, it predicted that it was generated, right? That was our loss. In the generator, when we give it a generated image, it should predict that it is a real image. And that's one of the key ideas, true labels. So it's backwards from before, right? Remember, before, when we gave it a generated image, our discriminator predicted that it's generated. But we now want to compute gradients such that our generator is updated in a direction such that the loss of this thinks that it's true. So we want to make sure our discriminator thinks this generator is a true image. And so this is going backwards against the grain of what the discriminator is trying to do. And it's such a, again, another small but such a crucial detail in the GAN implementation, right? We want to make sure that we update the generator in the direction that makes the discriminator think that this is a true label. And that's the key idea. Now that we have all of this, we can do, we can go ahead and store that loss. We can do generator epoch losses.append generator loss.item, just like before. And we can now do, and here's another key detail, generator optimizer.zeroGrad. So this is our sanity check. Granted, we don't have any gradients on the generator in this case already because we already zeroed them out in the previous step. But you know, for sanity's sake, there we go. We did a detach right here. So there was no gradients, but either way, for sanity's sake, we're always going to make sure we zero grad before we compute new gradients, as it always makes sure we're computing fresh gradients for the iteration that we care about. And then we're going to do a generator loss.backward. When we compute this generator loss.backward, remember, our generator loss is coming from the binary cross entropy, which means we're going to compute gradients on the discriminator and gradients on the generator. We have to go through this entire pipeline for us to compute gradients for the entire thing. But we're going to update the generator only and ignore the discriminator. We don't want to update the discriminator. Although we have gradients, we need those gradients to compute our chain rule through this order of operations to the generator. But we don't want to actually update the discriminator, which is why we have two different optimizers. We can do here generator optimizer.step. Right? That's why we have two different optimizers, because this will ensure that even though we have gradients on the discriminator, this generator optimizer only optimizes our generator. So only the parameters of the generator are updated here with those gradients. And again, the crucial idea is that we computed the BCE loss such that our generator's predicting data, we want to update the generator in the direction such that it generates fake data that makes the discriminator think that it's real, even though it's not, right? That's such a crucial idea to keep in mind. And I would really sit down and think about this before you keep going, because it's so important. It's basically fundamental to our entire implementation, to the entire GAN kind of setup. And so there we go. We have now updated our optimizer. But again, remember, by doing this generator loss.backward, we have inherently computed some gradients on our discriminator. Right, so the discriminator has some gradient information. Luckily for us, in the next iteration, we're going to zero those gradients out before we compute brand new ones, right? When we're trying to minimize the discriminator again. And so again, this is the kind of the simplest way we can do all of this. And now that we have all of this done, once we've completed an epoch, now it's basically just housekeeping. So now there's nothing more complicated. We're going to do generator epoch losses. Is going to be, we're just going to average up our loss for the generator in this step, generator epoch losses, and then our discriminator epoch losses is again, we're going to average up our discriminator loss for this specific epoch, discriminator epoch losses. Now that we have all that, we're going to say if we are, if we're doing if epoch percent plot loss frequency, so every 20 steps in our case, we're going to go ahead and just print this out. So I'm just going to copy this line here. Right? It's going to just go ahead and print out what epoch are we on, what's our generator loss, what's our discriminator loss, nothing crazy. And every once in a while, we want to make sure we generate some pictures, right? That's important. So we can just see what the generative quality looks like. So we're going to do if epoch percent mod plot generation frequency is 0, right? So every, I think I set it to 50, so every 50 epochs, we're going to generate some pictures. We're going to do generator.eval, so we're going to throw our generator into evaluation mode because we do have those dropout layers in there, so we want to make sure dropout is turned off when we're doing the generation. And then, of course, with torch.nograd, because we don't need to do anything, we're going to basically pass some noise to our generator and just plot what we see. So we're going to do noise sample torch.randn. So we're going to generate some noise here. I set ahead of time that I wanted to generate 10 images per generation. So we're going to do that. We're going to do 10. So it's num gens by our latent dim. So this is our noise sample, and it's going to be on the device just like earlier. We're then going to do our generated images is going to be the generator, pass in the noise sample, and then we're just going to move it to the CPU, right? So it's off the GPU if we're training on the GPU. And let's just go ahead and create a plot, fig, let's see, plt.subplots, and we're going to have one row by numgens column. And let's do fig size. I picked, what did I pick? 15 by 5? Okay, fine. 15 by 5. So it's just plotting stuff. And then we're just going to loop through each of the images and plot them. We're going to do for I in range numgens. We're going to do image is our generated images. Images I. So we're going to grab the ith image. And we're going to, so again, remember our data, our images is going to be in the shape of batch by 1 by, or actually in this case, it's batch by, batch by 1 by 28 by 28 because we already reshaped it in the generator. So that's what our data is going to look like. When we grab it, when we grab one image at a time, it'll automatically loop through. So it'll be, each image will be 1 by 28 by 28, and I don't need the 1 here, so we can just make it 28 by 28. So we can do a squeeze here. Squeeze, that'll get rid of that extra dimension. And then remember, our images right now are between -1 and 1 because we applied a tanh function to it. Now the thing is that matplotlib will not be able to plot -1 to 1. It expects 0 to 1 or integer 0 to 255. So let's just make it 0 to 1. So if we have -1 to 1, we're going to undo that normalization that we did earlier. So if we have -1 to 1, if we take -1 to 1 and we add 1 to it, so if we do +1, then we'll end up with 0 to 2, right? That'll be if we add 1. And then if we divide by 2, that'll give us 0 to 1, right? So that's how we ensure we convert our -1 to 1 pixels to 0 to 1 pixel values. So let's go ahead and do that. It's going to be +1. We're going to add 1 to it. And we are going to divide 2, just like that. And so then we can store in this specific location, .imshow image, we'll make it a numpy array, and it's a grayscale, so we can do cmap equals gray. There we go. And then axi, we don't really care about the axes, so we can do set axis off. And there we go. And we can throw a plt.show in there so we can actually see it. And once we are done with our generation, we can then set our generator dot train, right? Stick it back into training mode so it can pick up, right? Continue training after this iteration. And then we can end this by, we can go ahead and let's see, which indent are we at? So back here, so it's just a single one. Return our generator, discriminator. We don't really care about the discriminator once we're done, right? Once we're done, it's all we really care about is generator. Discriminator is just there to help the generator get better. And disk losses, right? Just something like that. And so now that we have that, let's just go ahead and copy the rest of this in. It's just going to run this code cell. We can find bugs. So we're saying our generator, discriminator, gen losses, disk losses. We're going to pass in our generator, discriminator, the generator optimizer. Is that what I called him? The gen optimizer, disk optimizer. Yeah. So we have our gen optimizer, disk optimizer, our train loader, how many epochs we're going to train for, what device, how often do we want to plot, how often do we want to print. Let's see if there's a, looks like we have a bug. So discriminator loss is not defined. So let's take a look here. We have here our discriminator. Oh, I called it the disk loss. There we go. Another bug. Oh, right, of course. If I called it disk loss right here, then it's going to be disk loss right here. And we should be off to the races. Let's see here. Yep, there we go. So we can see that generation has now begun, right? So this is going to keep training. And actually, this doesn't always necessarily converge. So I'm going to talk about a couple of different problems that you'll typically see. One of them is mode collapse. So you can imagine that this training paradigm feels a little unstable. And the reason is mode collapse is one of them. And so mode collapse is a problem where your generator, let's say your generator, we have 10 different digits, 0 through 9. And so the generator gets really good at generating, let's say, digits 0 and 1 and 2, or let's just say 0. So the generator gets really good at generating zeros. And so the discriminator says, you know what, the 0 digits are really, really hard for me to predict correctly. So I'm just going to focus on the other ones. So I'm just going to focus on 1 through 9. And so the generator starts getting information saying, hey, like I'm generating all of these zeros super well, but the discriminator doesn't seem to care. It's focusing on 1 through 9. So I'm going to swap to another one. Let's say I get really good at generating 4s now. And the discriminator then says, look, the 4s are getting really challenging for me to generate. I can't do it. So I'll just focus on everything but the 4. And again, the generator say, oh, like I'm generating these great 4s, but the discriminator again doesn't seem to. And this kind of out of cycleness of the GAN setup it's called mode collapse. There's other types of training instability as well, which is why we'll be looking at some other methods like Wasserstein GAN, some other stuff that try to alleviate some of these problems, but GANs inherently are unstable. Whenever I do GANs myself, it requires a bunch of finicky effort to get it to kind of work well. So in my own implementation, it actually took a couple of different runs, maybe I think it took maybe 2 or 3 runs to actually get it to start to converge. And this is, again, a very standard problem you're going to see for GANs, that they're going to just be really good at generating like 1 or maybe 2 of the digits, and then other digits just suck. Or they just keep generating the same like weird looking digit every single time. And again, these are some of the training instabilities that cannot really be avoided in GANs using this method, the method we're looking at right now. So while this is training, we'll kind of see how it goes. I'll show what the results look like if we look at one of the completed notebooks, and you can see that it starts to generate some reasonable generations. You can see here it's got good at 1s, and then it's like 7, 1, 3, 4, 1, so on and so forth. And you can see as it's starting to train, you can see the diversity in the types of digits it's generating seems to expand. And this seems all well and good, except for one problem. I have absolutely no control over what's happening. It just generates a random digit. I can't tell it, oh, I want a 3, I want a 1, I want a 5. I have no say over what's being generated. It just simply generates something. And so this GAN is cool on its own. But what we're going to be looking at next time is how to add a conditioning signal. And so conditioning signals are especially important in generative problems. I'm sure you've seen those text conditional diffusion models. You give it a prompt like, I want a picture of a golden retriever running on the moon. And suddenly it can do that. And that's because the model has been trained to do text conditioning. And so there's a lot of ways you can implement conditioning signals in your models. What we're going to be looking at is some very simple ones, but we're going to end up doing all of them as we kind of go through the different types of generative models. So we'll see all of them. The main ones is concatenation, there's additive signaling, and then when you move into the transformers, there's cross-attention based signaling. So we're going to see all of that in the future. But the cool part is when you actually add conditioning signal, this is what we're going to do next time. There won't be too many new code things. We can start generating 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I can specifically state, I want this digit. Like I want a 5, I want a 6, I want a 3. And that additional information makes this a much more helpful generative model. Like I can actually tell it what to generate, which is nice. So let's take a look and see how you are going. So we can see this is a clear example of mode collapse, right? We can see our discriminator loss has completely collapsed. So the discriminator's gotten really, really good, and the generator's loss is kind of high. And this is a typical paradigm that you'll see when training. So you can see this is an example of when it worked. So this is a good, relatively good training. The problem with these loss plots in GANs is they're not very interpretable. You kind of just see them, and for the most part it's fine, but typically you'll see that like the discriminator continues to improve, get better and better, and the generator kind of also continues to improve because it goes in the opposite direction. But the other way around. The generator continues to improve, and the discriminator, you can see the loss kind of gets worse as it goes. And at some point, the model kind of, you can see here, it took about 40 iterations for it to not be so good, and then it picks up from where it left off. So again, training GANs is a very unstable paradigm. We could let this run. We could run it a couple times, and you'll see that it'll work sometimes. It may not work sometimes. That's just the reality of it. So just a quick cut here. So what I did, I just reran exactly the same code. I didn't change anything, but now you can see it's starting to generate some reasonable images. So in the first example, you saw mode collapse happening. The instability was kind of on display about the GAN, but rerunning it again, it seems to be working. So this is again a little bit of that give and take when it comes to GAN, some of the annoyingness that I find about training them, and again why diffusion is just so nice to train, because typically you don't see some of these instability issues where different runs give you such different results. Now there are a few things we can do to actually improve on this that we will be looking at later, but for now this should give you a general idea. You can start to see, again, a little bit of that mode collapse. Look at the generators kind of focusing on 7s and 9s, right? So it's totally not a completely perfect system, right? The GAN has some issues that other future papers have gone on to at least address. But this is kind of the vanilla GAN, right? We wanted to set the stage with something simple just so we understood some of the architecture, because 90% of the code will look basically like this, right? Whether or not we're doing it here for more advanced implementations, it'll look basically like this. So I just wanted to set the stage here. And in future videos, we will be looking at how do we make this better, right? So either way, I'm gonna call it here. I will see y'all in the next one where we implement a conditional GAN.